you going to write? Oh, cool. So, yeah, it's great to have Po-Ling from Cambridge University, and who will tell us about robust statistics.
That's brilliant.
Okay, thanks, Misha. So, Okay, so I'm going to be talking about robust statistics and maybe generalization. So the other bootcamp organizers asked me to give a talk on classical Huber theory. So that's what I'll do, and I'm going to try to bridge it to some maybe more modern topics and things that I and collaborators have worked on. And we'll see how far I get. I have quite a bit of material, and I'm happy to sort of subsample it and see what people are interested in. So maybe a very brief intro. Well, the foundations of robust statistics can be traced to folks like Huber, Hampel, Tukey, etc. in the 1960s. So, when we're talking about classical, we're saying like about 80 years old. And roughly speaking, we want to deal with deviations from model assumptions. Okay, and also develop procedures that are reliable. And reliable could be in terms of accuracy or efficiency under contamination. Okay. And if you want some references on the classical stuff I'll go through, just search for these people and their textbooks, and you'll find lots and lots of information. So what we're going to open with is M-estimation. Okay, so M-estimators for location estimation. All right. And what I'm going to talk about is focusing on the one-dimensional setting. Now, this might seem sort of boring, but there's a lot of elegant and interesting statistical theory that starts from this. This comes from a paper by Huber from 1964. And the setting is the following. So we assume that we have x1 up to xn, and these come IID from what's called a parametric location model. So we'll write it as ft minus theta, which is f theta of t. So think about f of t as some CDF. This is where ft is a CDF, and we want to estimate the unknown parameter theta. So as a concrete example, we can consider f of t is equal to the standard normal CDF, which means that we have data, IID data, from normal theta 1. The PDF looks like this. We want to estimate theta. Okay, so what would we do? Well, I mean, if we're trying to estimate the mean of a normal distribution from IID observations, we would use a sample mean, right? Okay, so, well, and this is a little bit more general. So if the PDF of f is symmetric around 0, so oops, around 0. So in other words, the shifted distribution f theta is symmetric around theta, then the sample mean is clearly unbiased. Okay, so if we look at expectation under f theta of 1 over n sum xi, I goes from 1 to n, then we get back theta. Okay, because if it's a symmetric distribution around 0, then it's unbiased for 0, and if we shift it by theta, it's unbiased for theta. But the question is, so is this the best thing to do? Is this the best estimator when the data are contaminated? Okay, so now we need to talk about what it means for data to be contaminated. And you'll see this very classical definition of the Huber contamination neighborhood. F is known. Yeah. I mean, if F were unknown, it would still be fine if it was symmetric. But I guess for what, well, I mean, for what I'm going to talk about, F is sort of like standard normal, and we talk about the best possible loss. So in order to construct the best possible loss, I suppose you should know what phi is. Okay, so define the class of distributions, or maybe I'll say the uncertainty set of distributions in the following way. So we'll call it P epsilon of some reference distribution, F0. And this will be equal to all CDFs F, which can be written as a mixture of F0 plus epsilon H, such that H is a CDF. Right? So another way to think about it is that now you have a mixture of the clean data distribution and an arbitrary distribution. So if you haven't really seen a lot of robust statistics and you just know some buzzwords here and there, there's been a big wave of work on adversarial contamination, and everyone will say, Huber isn't adversarial. Well, it is a little bit. So we may comment a bit on adversarial contamination later as time permits. But what is sort of adversarial is that our uncertainty set has a mixture with anything, not just some fixed class. Okay, so this is what's often called Huber's epsilon contamination neighborhood. And maybe just a small note. So I'm going to focus on the Huber model, at least for the first part of this. But I mean, if you haven't seen much of robustness, you might ask, like, how about other neighborhoods? And other neighborhoods have been studied. In classical robust statistics, people looked at the Kolmogorov neighborhood. But not as much as the Huber neighborhood. So maybe one small remark is that if you look at F in this neighborhood around F naught, then what you can see is that if you look at the Kolmogorov distance between F and F naught, then an easy calculation will tell you that this is also bounded by epsilon. I don't know if everyone can still see this, but okay, so maybe I'll just doesn't move really easily. Okay, so this is a simple calculation. You would just say that an F which is in this neighborhood can be written as 1 minus epsilon times F naught plus epsilon times H minus F naught. There's a T in here too. Okay, and then a simple application of triangle inequality should give this bounded by epsilon. Okay, so that's like a small arithmetic calculation. Another remark is that, in fact, the total variation distance between F and F naught is also bounded by epsilon. Okay, but this is not really important for what I'll talk about next. All right, so I promised something. So I've told you about location estimation. Now, what are M-estimators? Well, in the computer science world, oftentimes M-estimators go by the name empirical risk minimization. So we have some loss function. And we want to minimize the empirical loss. So here's a definition. Consider, and for the purpose of what I'll talk about next, we'll make it symmetric. So since we're in one dimension, the loss functions are just going to be univariate. And a minimizer, which we'll denote by theta hat n, which is in the arg min over theta of the sum I goes from 1 to n, L of xi minus theta, is the M-estimator associated with L. All right. So before I start to talk about any robustness, let's just understand a little bit, what are some sorts of losses that we may be interested in. So here are some quick examples. The first one is if L of t is equal to quadratic, then theta hat n is the sample mean. Okay, so that's easy to see. You just take your quadratic loss, you differentiate, you solve, and you get the empirical mean. The second one is if L of t equals the absolute value, then theta hat n is sample median. It may not be unique, but if you have an odd number of data points, well, okay, yeah. So if you have it depends on it's in terms of an order statistic. If you have an even number of data points, normally you think of a sample median as the midpoint. But if you're minimizing the subjective, it's anything on that segment in between the middle points. And then what is going to feature more heavily in what I'll talk about, there's one more estimator, and I'll draw it first. And this estimator sort of starts out like the quadratic, and then it looks more linear. So it looks like this. It's quadratic, and then it's first order differentiable, so it becomes linear after that at some point gamma. And this is called the Huber estimator. So if this is L gamma Huber of t, then we have the Huber estimator. And let me write out algebraically what that is. Then theta hat n is the Huber estimator parametrized by gamma. And what it looks like is L hat Huber, or L gamma Huber, is equal to t squared over 2 for absolute t less than or equal to gamma, and then it becomes linear. Gamma absolute t minus gamma squared over 2 if that thing is true. Yeah?
Can I ask a silly question? Mm-hmm. Why is symmetry important?
It makes the problem easier to solve because I'm going to prove something about optimality. Well, I won't prove it. I'm going to state something about optimality. And the asymptotic variance of the estimator is much easier to write down in closed form when things are nice and symmetric. I mean, the two play off of each other. So we need to know what the limiting distribution of the M-estimator looks like. And if we have symmetry in both, then everything's great. Yeah, so I guess what I want to yes, Misha. Minimize or maximize. Just like an ERM, right? Yeah. Okay, yeah, so what I want to convey, sort of maybe one important take-home message, if you don't remember anything from this classical overview of robustness, is why Huber. So, I mean, I know that in sort of robust statistical learning, right, Huber shows up, but statisticians really like Huber. So one thing I want to convey is why Huber is a good thing to do, at least in one-dimensional for symmetric distributions. Okay, all right. So yeah, now we'll talk about sort of optimality of Huber loss. Okay, and we'll put in another nice buzzword, Minimax perspective. Okay. So maybe let's pause for a moment. So when we were talking about estimating the mean of a standard normal distribution, and I said, okay, well, we have these sample means, and I said, if we have robustness, is there something better? One thing a small leap in logic is some claim about the sample mean being the best estimator if we didn't have contamination. All right, so this is sort of classical statistical theory, which is that so the sample mean in the case when data were, maybe I'll use another color now, right? So if the data are normal, theta 1, then it turns out that the maximum likelihood estimator is given by the sample mean. And why do we like maximum likelihood estimators in statistics? It's because they have the minimum asymptotic variance amongst all asymptotically unbiased estimators. Okay. So, but now the thing is, well, we have data, and they're not necessarily coming from the clean normal distribution. They're coming from some ball around the clean normal distribution. So we want to understand, what is the asymptotic variance we get when we're looking over this whole class. So to that end, we need to know what is the asymptotic variance of some M-estimator with a certain loss under some distribution F. Okay, so I'll write down a non-rigorous version of a theorem. Okay, so here's the theorem. And the theorem says that suppose L is convex and symmetric, and the distribution of F is symmetric around 0. Okay, meaning in our location model that F theta is symmetric around theta. Then under regularity conditions, which I'm not going to state, we have the following. Square root of n, let's see. So if we have xi coming iid from F, then square root of n times theta n hat converges in distribution to normal 0. And I'm going to write it like this. So in robust statistics, we often care about the derivative of the loss function. Okay, I hope everyone can still see this. This is where psi is equal to L prime, right? So let's just sort of soak this in a little bit. So you're looking for a convergence of the M-estimator, theta hat n, to the true parameter. So you might think, where'd the true parameter go? Well, we're assuming that we've sort of recentered everything so that we're estimating 0. Right? So we really want to estimate theta, but we've shifted everything. And if it's distributed according to some distribution centered around 0, we want to know how quickly does my M-estimator with a particular loss converge to 0, converge to what it's estimating. And this is the nice form of what the asymptotic variance looks like. Now, this is a special case of a much more general theorem, which can deal with asymmetric distributions and loss functions that don't satisfy the same regularity conditions. I'm not going to write down the regularity conditions, but I mean, as a first pass, it better be differentiable. But there are some other things it needs to be as well. Okay. All right. So what does this give us? Well, it gives us some kind of expression to start to deal with. So just to remind you, and I'll write this down more precisely in a moment. Right. We want to understand how does this variance this variance behave if I fix a particular M-estimator, let's say the Huber loss, and I want to look at how big the variance can get in the worst case distribution in a ball around the nice uncontaminated distribution. So let me write it down over here. Yeah.
This theorem applies to all of the losses you have there, not just the Huber loss. Is that right?
Yes, yes. I think it doesn't quite apply to this one because it's not differentiable, but some version of it applies to this. The more general theorem applies to this. Yeah. But yeah, that's a good point. So there are regularity conditions that are mysterious because I haven't told you exactly what they are. But amongst this class of estimators, that's what we care about. So maybe just a little bit of, yeah, Misha.
You need to, then this, technically this would become infinite, right? But somehow maybe you don't care that. I guess.
I mean, it depends. Yeah.
Put the derivative on the outside of the expected value.
Of the expected value.
And then that's it.
Yeah, but it's easier to, well, what we manipulate for the optimality, right? What you manipulate is this. So in order for it to actually be optimal, then you have to be able to interchange derivative and integral. Yeah. Okay, so, right, so this is the thing we care about. So we're going to call this V, the asymptotic variance, and it's a function of psi and f, right? So I considered writing it as a function of L and F, but then there's just too many L primes that float everywhere. Okay, so what we want to solve the following Minimax problem. So take a min, I'll take a max of V of psi f. And the max is going to be f in some ball around a distribution. We're going to use standard normal. Okay, so actually, Huber loss is optimal if you use standard normal. there's a more general statement that says what the right loss should be if you use a different distribution, but let's deal with standard normal. Now what's the max over? The max is over all psi in some nice class. So you might not like this very much, but let's call psi this nice class satisfying regularity conditions. Okay. In particular, I mean, it includes Huber, it includes the quadratic, which gives you the empirical mean. I think it includes anything that's sort of, first order differentiable and maybe second order differentiable up to some finite number of points, and probably much more general than that. Okay, so this is the problem we want to solve. And maybe before well, I already told you the punchline. I already told you that the best thing is Huber. But like from this point of view, we can also kind of try to understand, well, what are the shortcomings of something like a sample mean, right? And that also kind of motivates why Huber. So suppose that we take L to be equal to quadratic, right? So we're looking at a sample mean. And then in that case, psi of t, which is the derivative, is equal to t, right? So maybe we'll go over here. So this formula here allows us to evaluate what the asymptotic variance looks like. Okay, so in this case, we have v psi f, and that should be equal to the expectation under f of xi squared. That's on the top. And then psi prime is just 1. So on the bottom is just 1, right? And so now if we take f is equal to 1 minus epsilon phi plus epsilon h, where h is some arbitrary CDF, then that means that that v of psi f is equal to 1 minus epsilon times the expected value of xi squared under the standard normal, which is 1, plus epsilon times expectation under f of, expectation under h of xi squared. Right? So the point is, yeah, question.
Is it an arbitrary CDF or is it a symmetric CDF?
Oh, yeah, sorry, yes. For this calculation to be valid.
So also over there, the script piece of epsilon is also.
It's also over symmetric, yeah.
So the neighborhood is all symmetric.
Yes, everything is symmetric. Yeah. Yeah. Okay, so yeah, but that's still, kind of, I mean, it's not completely average case. It's sort of worst case amongst symmetric distributions. Yeah, yeah.
Because the asymptotic variance would no longer make sense.
Yeah. Right. Okay. So the point is, if you let these xi's be drawn from this mixture where h could be running off to infinity in a symmetric way, then this thing can go to infinity if h is if h is arbitrary. Right. Okay. So the question is, what could you do that's a little bit better? Okay. So now suppose that psi, which is the derivative of the loss, satisfies the infinity norm. So basically, psi is a bounded function, and it's bounded by gamma. Okay, and just to maybe going back to this Huber loss. So if we look at this was L, if we differentiate it, we end up with this. Right? So it's linear, and then it's constant in the constant parts. That happens at gamma and negative gamma, and the value is gamma. Okay, so the suppose that psi satisfies psi infinity less than or equal to gamma is suggestive, because that's what happens in the Huber loss case. And what happens to our calculation? Well, in that setting, we're looking at, again, v of psi f, and that's going to be equal to 1 minus epsilon times expectation under phi of psi squared of xi plus epsilon expectation under h of psi squared of xi. So that's on the numerator, right? So I'm just writing the numerator, which is the expectation under f. F is a mixture of the clean distribution phi and a contaminated distribution. And I can do the same thing on the bottom. So I have 1 minus epsilon expectation under phi of psi prime of xi plus epsilon expectation under h of psi prime of xi, and I do this all squared. Okay, and the point is that I can now upper bound this. And the simple upper bound is 1 minus epsilon expectation under phi psi squared of xi plus, and because psi is now bounded, there's epsilon gamma squared divided by, and yeah, sorry, I guess you have to stare over there. Yeah, okay, I'll move over there. I'm starting to miss the boards where you can go up and down. Okay, so if we continue this bound, I'm just going to upper bound this term by gamma squared and forget about that term. That term is something positive. So this is upper bounded by 1 minus epsilon expectation under phi of psi squared xi plus epsilon gamma squared divided by 1 minus epsilon squared expectation under phi of psi prime of xi squared. Okay. And the point is that this is now bounded. So if I let h go off to whatever it is, you know, the fact that psi was bounded means that anything involving h on the top is bounded. Yeah. Because it's convex, right? Because L is convex. Okay, so this is a motivation, not a proof that Huber is a good thing to do. I'm not going to actually prove that Huber is the best thing to do, but I'll just say that so the result, which was one of the main results, but not the only one in Huber's 1964 paper, is that the Huber loss, maybe I'll write it in this way, L gamma Huber solves the Minimax variance problem. Where gamma is related to epsilon via some implicit equation. Okay, so that's sort of important result number one, and quite possibly the most important result if this is your only time dipping your toes into robustness. Yeah.
What if you not be the Gaussian arbitrary symmetric distribution? Would you get some kind of convergence thing where the optimal result, optimal loss is the median at the L1 loss? Or?
So Huber has a formula for log concave, symmetric log concave distributions. So yeah, I mean, you could probably construct something for which median is the right thing to do.
Is it like, you know, is the median some kind of extreme case where if I were much more adversarial in my max there, and I just said I'm going to take a max over all symmetric distributions or something like that?
But I mean, we're already taking a max over symmetric distributions, but in the Huber ball. Are you saying you want to move away from the Huber ball as well?
Yeah, let's say instead of B, I have arbitrary symmetric distribution. So I mean, we could just replace that max with max over symmetric distributions.
But it should be around something, right? Or I mean, at least the Huber analysis is like it's around something. So yeah.
I mean, I could make epsilon infinite. Make epsilon 1, I guess.
Yeah. I want to say the median is then the right thing to do, but I might be wrong. Yeah. Yeah.
How tight is this upper bound?
How tight is this upper bound? This can actually be achieved here, because you basically say what you need to do is you make sure that H puts mass just sort of far away, because.
So then all you did is showing that the other direction that figures the loss.
But it has to be best over all possible loss functions. Yeah.
So Huber achieved this with equality.
Yes, Huber achieved this with equality, but even better than that, it's the best possible. And then, so basically Huber constructed a solution to the saddle point problem. And that, so basically Huber constructed a solution to the saddle point problem. And that involves And he has a construction that works for a general log concave symmetric. But going back to John's question, you want to look at a ball around a whole bunch of stuff. Well, I don't know what you wanted to do.
It's like, if we're going to be really robust, just any symmetric distribution.
Yeah. Not sure off the top of my head.
There's like a median type flavor in all of the cases, like this linear segment. Well, yeah, no, I mean, I actually don't know. I mean, the median, there could be distributions that are symmetric for which the median actually is undefined, right? You just have no mass near zero, then the median's undefined. So maybe the median's not the right solution. I think in that
Yeah, median could be a bad thing to do with, like, a bimodal distribution.
Right, but they're also the Huber laws will have the same thing if the modes are far enough apart. So maybe it's the case that there's just no solution.
I'm not sure. I mean, so there's a whole theory of sort of why when the median is the best thing to do that Huber also had, and this is more for the bias rather than the asymptotic variance. But yeah, I mean, in some sense, the median is sort of a limiting object for Huber loss.
For sure.
Yeah. Okay. Anyway, so right, what was I saying? I guess what I was saying is this is an important take-home message. Now you all know why Huber is a good thing. Okay, but Huber is also a good thing from another perspective that I'm only very briefly going to touch on. So in classical robust statistics, there's another camp, and this camp was very much, I don't know, introduced or progress was made in PhD thesis of Hampel, and so the difference between them is that Huber is solving, maybe I should write this down again. So we're trying to do a min over psi, a max over f in some ball around a nice distribution of this minimax, of this asymptotic variance. And here epsilon is something small, but it's fixed, right? So we have some fixed radius of the uncertainty ball. We're trying to solve this problem. And depending on what the value of epsilon is, it tells me what the right gamma is. But you might also be interested in cases where epsilon is tending to 0. And that was the interest of Hampel. Okay. So Hampel looked at things in terms of functional derivatives. So we assume that we have a sequence of estimators. How do we want to write it? So maybe I'll write it in theta hat n x1 up to xn, which are converging to some function of f. And this is where the xi's are distributed IID according to f. Okay, that's like bad notation. So this is converging in probability when xi is coming IID from f. Okay, and Hampel's theory sort of focuses on what is this limiting value t of f, where I allow my data to now come from an IID mixture of f with something else, and I send epsilon to 0. So concretely, it's written in the following definition. The influence function, and I really dislike the notation, but okay, so this is some function, and it's a function that maps from R to R if we're only in the univariate case, is defined as influence function in the direction of f is equal to the limit t goes to 0 of t of 1 minus tf plus t delta mass at x minus t of f divided by t. Okay, so it has some flavor of this Huber mixture. So we're still drawing IID data from a mixture distribution. And the mixture is, so maybe f is like our standard normal, and we allow ourselves to draw with probability t from some contamination point mass at x. All right, and we look at this as a functional derivative. And this value is going to depend on what direction we're contaminating in. And the point is that, well, at least as a first pass in Hampel's theory, an estimator is declared robust if this influence function is bounded no matter what direction you go in. So let's write that down over here. Where did my eraser go? Yeah, thanks. Okay. So an estimator is robust if the gross error sensitivity is bounded. And what that means is that if you look at a supremum over x of absolute IF of x TF, then this thing should be finite. Okay. And we're not going to go much in this direction, but the one thing I want to say is that for M-estimators, satisfying regularity conditions, one can calculate the form of the influence function. And what you have is that the influence function in direction x of t f theta is proportional to psi of x minus theta. Okay. This just means a point mass at x.
Oh, the x is actually a point.
Yeah. For any x that you do a point mass at x, you let x be anywhere, and you want this thing to be bounded no matter where x is. You make the contaminating part go to 0. Yeah, so this is the part. So t is now taking the place of epsilon. And unlike the Huber case where we had a fixed ball, small epsilon, but not vanishing, now we have the contamination is vanishing.
You're only allowing contamination by point mass.
Yeah. But the point is that, I mean, if this functional has a linearity property, then if you want to know how much you contaminate by a general distribution, you sort of integrate the influence of individual points. Okay, so going back to M-estimators, the point is, and I'm not going to say much about this influence function which we want to be bounded. So maybe just to draw this, right? So as we were just saying with Misha, right? X is this point at which you're contaminating, maybe a nice distribution here. Say this was normal 0, 1, and you're letting x go wherever you want. So then the influence function will be a function of how much does your estimator change as x walks away. Okay, and it turns out that this is proportional to psi. So in particular, well, if you remember the sample mean, right? The sample mean had psi. Psi is just linear because it's the derivative of the quadratic. If it's a Huber loss, then it's going to be truncated like that. All right. So we see that, if we're just doing a sample mean, then if you make x go further and further away, the amount of influence it has on the empirical mean, it is getting worse and worse. But Huber stops that at some point. Okay, so sort of as a first pass, without going into details, we see that, again, the Huber loss is robust in a way that the sample mean is not. And furthermore, and this I won't go into, the Huber loss is actually also optimal under this sort of framework. So let me just say one small statement about that. Okay, so Huber loss was also shown to be optimal for in the influence function framework. And what does that mean? It minimizes asymptotic variance subject to a bound on the gross error sensitivity. I don't want to say gamma, so let's say gamma tilde, right? So this is a sort of reason number 2 for why statisticians like Huber. So if you think of a different framework of robustness, it's still sort of an optimal thing. Okay, so now maybe to bridge from the classical robustness to some more modern things. So I'm going to attempt to draw connections to a few things without seeming all over the place. Yeah.
What happened to the parameter of the Huber loss then?
The Huber loss is going to be connected to what the upper bound is on this gross error sensitivity. Yeah.
Are these two perspectives close enough that you can even use lemmas or part of the proof of one with the other? Because you will both go out with psi and
No, because one of them sort of has this fundamental, like t is going to 0, and the other one has a fixed radius epsilon. I mean, you can try to relate one to the other to say that one should be a consequence of the other if epsilon is going to 0, but it's sort of the best you can do. Okay, so now let's say a little bit about unconventional M-estimators. And by unconventional, I mean now let's move away from this nice, convex loss and differentiable and all that. So the first thing is just sort of a comment, again, to place things into historical perspective. So just a word on non-convex or so-called redescending M-estimators. Okay, so far we've looked at losses that are convex, but maybe we care about losses. Like, let's keep the symmetry for now, but we might want a loss that's not convex. So these were studied historically to have a finite rejection point. Okay, and maybe I'll just write this out. So we call the rejection point as the infimum of r greater than 0, such that the influence function xtf is equal to 0 when absolute x is bigger than r. Okay, so it's saying that if we put our contaminating mass far enough away, then we're just going to ignore it in our computation. And you'll see that, well, this sort of happens if your loss function becomes constant after a while. Equivalently, so this is my loss function L. Equivalently, what does the psi look like? Well, psi is going to be something that maybe looks kind of like, all right, so at some point, it goes down to 0. It's a nice odd function because this one is symmetric. And so if you're trying to solve the M-estimator, then equivalently, you could say that you're trying to solve some I goes from 1 to n of psi xi minus theta equals 0, right? You're trying to minimize the loss function, empirical loss, so loss applied to xi minus theta, and equivalently, you can take the derivative and set the so-called estimating equation, the sum of the psi is equal to 0. And if psi becomes 0 for large enough points, and that means that if you take something that's big enough, then it's not going to affect your estimator at all. So that's why historically people cared about these so-called redescending estimators. And they're called redescending because the psi function sort of goes back down to 0. And I'm only highlighting this because, well, part of it is that personally I like non-convex but not too non-convex optimization. But one very interesting result about redescending M-estimators is that although it might be hard to find a global optimum of a non-convex thing, it turns out that if you just care about asymptotic properties of the global optimum, you can get that by finding a local optimum or close enough, something that's close enough to the solution and taking one gradient step, and you have the same sorts of asymptotic results. So I'll just mention this. So asymptotic normality. Let's say using a local optimum or even a Huber estimator as initial point, then taking one gradient step, was studied in a paper by Bickel in 1975. And I sort of think of this as a precursor to lasso debiasing, which was a very hot topic in statistics from around 2018, plus or minus. 2018 seems late. Is it like much earlier? 14? 15? Yeah. Plus or minus. Yeah. Okay, but I'm not going to say too much more about this. All right, so here's the part where I want to mention some of my work with Ankit and Varun, who are both here. This is only loosely connected with what I've been talking about with M-estimators. But I guess the point of this sort of next cameo is to maybe give you something exciting, right? Because you're just like, yeah, okay, this stuff is 60 years old. And okay, so now let's talk a little bit about the Shorth estimator. All right. And this is, oh, thanks, Matthias. And so this is work by Ankit, who is here, Varun, who is here, and me. And it first appeared in an ISIT paper in 2019. And the setting we were looking at was where you have n independent samples. Xi comes from some distribution pi, where each pi is symmetric, and there's a common mean mu. Let's call it mu star. I should say symmetric, and I think for our work we needed unimodal. Okay. With a common mean mu star, and the pi's are unknown a priori. Okay, so this is sort of a modern setting. So now you have data. You just have one sample from each distribution, all right? And what's in common about these distributions is that they have the same mean. So maybe it looks like this. You have, this common mu star, and maybe you have one normal, then you have another normal, and you have another normal. And the question is, how well, or what are some good estimators that will allow you to estimate mu star with a reasonable accuracy? So here we see that the mean is unbiased, but probably not the best thing to do, because if the variances sort of run off to infinity, then that's bad. Okay, so we studied two estimators. So the first one is what's called the R modal interval estimator. And this estimator was also studied by statisticians in the robust statistics era. And what this does is it outputs the center of the most populated interval of radius r. Okay, so what that looks like is, yeah, I think I can write one more thing. So if we define f of xr of z to be the indicator that x minus z is less than or equal to r, and we define Rn of f to be equal to 1 over n times the sum I goes from 1 to n, f of xi, then let me go over here. Then we take our modal interval estimator, let's call it mu hat r modal, and that will be something that maximizes Rn of fxr. Okay, so what we're doing is we're building this, what are we doing? We're sort of building a histogram, right, with length r, and we're trying to see what is the point that maximizes the histogram that we build. And then the other estimator that we look at is what's called the k shortest gap estimator, or k shorth estimator. And this one gives the outputs, the center of the smallest interval containing k data points. Okay, so there's a way of writing this with the formalism that we had here. So if we write rk hat to be the infimum over r, such that supremum over x of 1 over n, sum I goes from 1 to n, Rn of fxr is greater than or equal to k over n. Then we define mu k hat shorth to be equal to the argmax over x of Rn fxr. Okay. So we look at these histograms with length r of the bins, and we want to pick up at least k of them. Okay, so maybe as an example, if k is equal to 2, then you're just looking for the shortest gap between points. All right, so as an example, if k equals 2, find center of shortest gap between 2 points. Okay, so the idea is that you have your data, and it's kind of spread out. Maybe that's too suggestive, but so you would output that guy. All right. So it turns out, and I'm not going to go into the details, that these are both good estimators in this setting where we have data that are not IID and are highly heterogeneous. Okay, so sort of the main result is that the behavior of the modal interval and shorth estimators depends on the order log nth largest variance. Okay, and this is different from, let's say, an empirical mean, where the variance of the empirical mean is clearly going to be influenced by the worst distribution, right? Yeah, Ankit, did I say something wrong? Yes, thank you. Yeah. Right. So you're going from the bottom rather than the top. Okay, but why is this interesting? I mean, again, I'm not going to go into details here. Well, so these estimators, you can think about these as sort of unconventional M-estimators, right? Because you can think about this as sort of a loss function that's a step. Yeah. So you have this. I guess I shouldn't do that, but you have this step here, and well, but you're maximizing. So think about the negative. So that's like a really, really bad non-convex, not differentiable loss, right? And for that reason, folks from the robust statistics community took a very long time to understand the behavior of the exact asymptotics of the modal interval estimator and the shorth estimator. So sort of historically, well, what happened is Chernoff had some derivations for the behavior of the modal interval estimator in his 1964 paper, where he showed order n to the negative 1/3 asymptotics. Right. So usually things converge at rate order n to the negative 1/2, and he showed that it's a slower convergence, and the limiting distribution is not normal. So then in the 70s, people looked at this shorth estimator. They looked at the setting of k equals n over 2. So this is the sort of more classical setting. So if you have IID data, then it kind of makes sense to look at the shortest gap, not between 2 points, but between some bulk of the data points. So it was shown empirically in the 70s that this seemed to be a very good thing to do. It was also shown empirically that it seems like you also have this order n to the negative 1/3 asymptotics, but people didn't really know how to prove it because you also had all of these, sort of bad behavior of the M-estimator. Yeah, question. I don't know that. I don't know. It's in this survey, Princeton data analysis, something by Andrews et al. Yeah. Yeah, so then a concrete proof of the asymptotics of the shortest gap estimator was proven by Kim and Pollard, right here. Kim and Pollard in 1990. And they have a paper called cube-root asymptotics. All right, so I guess I'm just saying that, it's, well, I don't really know how Ankit came across all the Shorth literature, but, the point is, like, it helps to know something about robust statistics, right? I mean, it sort of motivates different estimators you might look at, and in some cases motivates the analysis, not quite in our case. Another thing to note is that for our non-standard setting, the value of k that we used ended up being something like order log n. So because we have not IID data, it wasn't quite the setting that was looked at in classical statistics. Okay, so I will say one more thing, maybe two more things, we'll see. Let's start with one more thing, yeah.
So you could have also used the median, and then you're saying you will also depend on many variants.
Yeah, I don't remember exactly what the order is. Ankit, do you remember? Yeah, root n instead of log n, yeah. Thanks. Oh, I should also say that I'm not really acknowledging other people in the room who've worked on this. I think Nikita had some nice follow-up work. But yeah, do you want to say anything or?
Around.
All right, great. So maybe let me say, so let me talk a bit about robust hypothesis testing, because I think this is another interesting hypothesis testing. Interesting robustness direction. And I promised something that had to do with privacy, although that connection is a bit tenuous. But so reference here is a paper by Huber and Strassen in 1973. Okay, so in the 60s, it was all about location estimation regression, and in the 70s, some hypothesis testing. So suppose P0 not equal to P1 are two distributions. And we have IID samples, xi, and they come from a distribution P. Now, the P is either in an epsilon ball around P0 or an epsilon ball around P1. So we have hypothesis test, and H0 is that P is in the Huber ball around P0, and H1 is that P is in the Huber ball around P1. Okay, and for convenience, later we'll call this script P0 and script P1. And then the question is, what is the best test? And in order to define best, you need to, or in order to answer that question, you need to define a notion of best test. And the framework taken in this paper is known as the max-min test. Okay, and the max-min test is for a fixed error probability alpha. You want to maximize the minimum power subject to an upper bound on the level of significance. Okay, so in not words, what that means is take a supremum over all tests phi, and femum over p in the alternative class P1, expectation under P of phi of x, such that, am I losing? Oh, maybe I can squeeze that in here. Such that supremum over P in P0 of expectation under P of phi of x is less than or equal to alpha. And here phi is the test. So phi, based on observing data, capital X, makes a decision either 0 or 1. So that means null hypothesis or alternative. Okay.
clarify, these two neighborhoods could overlap, right? This neighborhood,
They could, but for our purposes, they don't. Yeah.
epsilon is sufficiently big.
Yeah. So the result I'm going to talk about is where epsilon is small enough. Yeah. So this is where phi of x is something in 0 or 1 defines the test. Okay, so if you go back over here, then we need that under the null hypothesis, or like anything in an epsilon ball of the null hypothesis, the probability of accidentally rejecting should be at most alpha. And at the same time, we want the best possible power. So under the alternative hypothesis family, we want to look at the best possible probability of rejection, right, where it's sort of the worst case in that ball. Okay, so that's this Maximin notion. And the main result is that for sufficiently small epsilon, the optimal test phi star is a likelihood ratio test between two least favorable distributions. And the distributions are Q naught in P naught and Q1 in P1. Okay. And let me now write down what some version of the result is. So here's the theorem. Suppose P naught and P1 have densities P naught and P1. Do I care about that? Okay. Respectively, then for epsilon greater than 0, small enough, the best test is of the form phi x1 up to xn is equal to 1 if, so it's a likelihood ratio test. You look at the product I goes from 1 to n of the least favorable distributions, q1 over q naught. You reject the null hypothesis if this is bigger than some threshold, and otherwise you do not. Right.
Are Q0 and Q1 data independent, fixed in advance, or do they?
Yeah, they depend just on the distributions. I mean, if you want, I can write down the form of them. It's not too hard to write down.
Are they the closest together?
Um,
Some like the algebra version?
They're sort of, well, what they are is they're sort of least favorable. So each one is, yeah, I don't think they're the closest one in, well, I don't know off the top of my head if they're the closest in a certain metric, but they do have some kind of a least favorable property. But let me tell you what the form is, right? So there's Q naught of x is equal to 1 minus epsilon P naught of x if P1 of x over P naught of x is less than some threshold, and otherwise it's 1 minus epsilon over b P1 of x otherwise. And similarly for Q1. So you see that they just depend on what P1 and P0 are and epsilon. But the point is, okay, so there's a constructive way to write down what Q is. And this leads to a particularly nice version of the test. So if you plug in what Q naught and Q1 are, then it turns out that this is equal to, so 1 if, let's see, 1 if, no, okay, let me just do this. Okay, So Q1 of x over Q naught of x is equal to A if P1 of x over P naught of x is less than or equal to A. It's equal to P1 of x over P naught of x if the ratio is between A and B, and it's equal to B if P1 of x over P naught of x is bigger than B. Okay. So therefore, the maximum test is a censored likelihood ratio test. Okay. So basically, I mean, it's a likelihood ratio test between these two least favorable distributions, but the same as saying, if I were doing a likelihood ratio test between the clean P1 and P naught, if it's bigger or smaller than the threshold, I truncate it. Okay, so the last thing that I wanted to say, I mean, this is sort of a nice theory in itself, but it turns out that, well, at least sort of conceptually, that there's some connection between this and privacy, kind of. Okay, so maybe just some comments on connections to differential privacy. Maybe I'll leave a question mark here, right? So one very active area of research that many people, including myself, are working on is connections between robustness and privacy. And I guess this is a tutorial talk. I should say what privacy is. So just bear with me if you know what privacy is. Just give me one definition. So a randomized algorithm, T, taking inputs in X and returning outputs in a space with events script S. Maybe I'll write it like this. Satisfies epsilon differential privacy if for all neighboring data sets, X and X prime, which have n data points, and all S in the script S, we have probability T of X is in S, is bounded by e to the epsilon probability Tx prime is in S. Okay, so this is the definition of differential privacy. It sort of says that the output of an algorithm doesn't change by too much if you perturb just one data point in your data set. So without really saying much more, I mean, you can see that this is something to do with stability and sort of like robustness. So there are definitely connections, some of which are more concrete than others, that say that robust algorithms can be easily privatized. Private algorithms are robust. So what I want to mention is more something that I've noticed from the literature rather than a very concrete implication. So there's this paper on private hypothesis testing. And the authors are Clement Canon et al. It's from Stock 2019. And what they're asking is, so setting is, suppose x1 up to xn are IID from P or Q, then what is the minimum number of samples needed for an epsilon differentially private test to distinguish P from Q. Okay, so they want to calculate some test statistic that is that satisfies this privacy condition, and they want to reliably distinguish P from Q. And I'm not going to go into the details of like exactly what it means for it to succeed, but the one thing I want to say is that so they study two different private algorithms. And one of them, which is optimal up to constant factors, is their so-called clamped log likelihood ratio test, where they look at the test statistic Tx, and they say you look at some I goes from 1 to n, log of pxi over qxi, then you truncate it between a and b, and you add some Laplace noise. Okay, so for anyone who's not seen differential privacy, I mean, basically you want to create some sort of a statistic that has a sensitivity bound, and then after that you can add some Laplace noise. And all I want to do is sort of compare, this sort of truncated likelihood and this sort of thing. And I mean, as far as I know, they came up with this test completely independently of the robust statistics literature. But I guess my point is, knowing something about classical robust statistics, even if the methods of analysis are not directly useful, could still be useful in terms of solving interesting modern types of estimation problems in the future. So I think I'll end there. Thanks for your attention.
Time for some questions.
Intuitive guess for this optimal Q0 and Q1 would be the worst contamination for P0 would be P1. The worst contamination for P1 would be P0.
Mm-hmm. I don't know off the top of my head. Yeah, I mean, I'm happy to. I have something written down. I don't have it parsed in my head. I'm happy to talk about it afterwards.
The balls don't overlap. You still have to be within an epsilon radius of P0 and P1.
Oh, it's not a common distribution, no. No, because one is in one ball and one is in the other.
Around the direction. Contaminating P0 in the direction of P1.
Talking about projection of P1 onto the ball of P0. Is it what you're saying?
Yeah, I'm not sure I'm not sure how to geometrically interpret it. Yeah.
About the classical setting where we talk about CDFs. Mm-hmm. Silly question. Why do we talk about CDFs when it's in 1D and that's like one-to-one with distributions?
I mean, that's just historically how they've discussed it. In fact, a lot of the theory assumes that there's a PDF too. So. And
then for this, I might have missed it, but how are A and B defined?
How are what and what?
A and B.
Oh, I mean, they're just defined in terms of they depend on epsilon and possibly P0 and P1.
It's not obvious to me, even when epsilon is 0, that this like Q0 lies within, like is like a 1 minus epsilon. Mm-hmm. P0 plus an epsilon. It's not obvious to me.
So the statement is that for epsilon small enough, there always exists an A and a B, so that these guys lie in there and they're least favorable in a certain sense. And you can prove that by some sort of continuity argument. Yeah.
Are those exact maximum tests, or are they?
Yeah, for like sample size n, yeah.
They're exact.
Yeah.
And it's not like as epsilon goes to 0, they become exact, right?
No, it's exact, yeah.
And so in the context of the hypothesis testing, the private one, is that an exact result or is that an asymptotic result, like order optimal thing? No, sorry, not the order, the private guy.
Yeah, it's optimal up to constant sample complexity. But I don't actually know the details. It's more just observing the relationship between them. Yeah, Nikita?
Yeah, so this clamping was more to put some one sensitivity just because then the idea is
Yeah, but you could say the same thing. Like, I mean, if something is robust, then it probably has a bounded sensitivity. I mean, that's like an intuitive thing, right? So then you can try to prove it, and then you can try to add some noise and make it private and try to prove it's optimal.
Just about this use of CDF, you didn't need the fact that there was a density.
Mm-hmm. For some of the results, I think you might. I mean, I didn't give you the proof of this Huber being optimal. I think it needs to have a density somewhere in there.
That would be a nice reason.
Wait, but regardless, the reason why the question is silly is because regardless of whether you need a density or not, at least in 1D, like a CDF has nothing to do with the density.
No, but I mean, just for you can always write down the CDF. So.
Yeah. I don't know. It's just historically that's the way it's presented. So.
Questions?
So
Thank you.